In this episode, we will show you how to measure project similarity with one of the methods that we have used and developed in Software Center. In our research team, we have worked with a number of different approaches to understand how to compare different projects. So this is usually quite a challenge because software projects evolve over time. The ways of working change, the technology changed, the platforms evolved, the teams evolved, and it's very difficult to capture that evolution because we could do interviews or we could do process analysis, but in the end it's difficult to capture that very objectively. So in our work, what we have understood from companies is that we could actually use defect inflows or Git commits as quite objective ways of quantifying software processes. I mean, those two data sources are quite nice sources of symptoms of software engineering project changes, because by the end of the day, what happens is that if you change your process, you have to change your testing. If you change your product, you have to change your ways of working and testing. If you change testing, then you change the defect inflow. And if you change defect inflow, that's going to show in the diagrams. But the problem in comparing defect inflows is quite tricky because the methods that we currently have are very much concerned about the fact that the defect inflows have to be aligned. They have the top of the defect inflows, this top and this top, they have to be quite similar. Those methods are very sensitive to starting at the same place, so the length of a zero or the first defect reported when it was reported could be quite different. It's also the length of the entire project that is quite tricky to capture in existing methods. So in our work right now, we have come up with a method how to do this comparison that is robust to those kind of changes. So we basically addressed two research questions: how to find how much processes have evolved. That's a very interesting question in itself. And which methods provide the best results. And here we compare our new method with a number of different existing ones. The SIMSAX method works like this. It takes the defect inflow, just as I showed you in the data. It divides that into window of a given size. In each particular window, it divides it into a number of bins and assigns a letter to each of the bin. If a data point finds itself in a specific bin, it assigns that data point to a letter. So in this example, it assigns the highest, the first point, the highest point, letter D. And it does so for all of the weeks in a particular sequence. Now, those parameters that we use are W, the size of the window, so how many weeks are used in the comparison, the number of symbols, the number of bins, so how many letters we assign to a particular defect inflow, and then the number of clusters that we compare, so how many letters do we use in a particular cluster. So first let us see a bit of data that we use in this exercise. We have chosen two open source projects. One is BERT and the other one is JDT. Both are coming from Eclipse, both have similar processes, but they differ. They differ in the total number of defects reported per week. As you see, the scales are a bit different. The shapes also differ. The beginning of BERT is a bit flat compared to the beginning of JDT, and also the ending differs a bit. BERT has much flatter curve compared to JDT. So we implemented this in Python in Jupyter Notebook. Here is a web version of the notebook. We need the standard libraries for machine learning, pandas, matplot, numpy, and also a specific library for SIMSAX bio. Now, SIMSAX comes with a number of different libraries that are already packaged as classes, and here we link in those to the project. Then the whole workflow starts by loading defect backlogs or git commits, and this is the way how it's done. So we have two classes that are specific, that extract this information and add some extra formatting in that. Then what we do is we import, here we check the format of the defect inflow. So we have, as I showed in the data set, the start of the week, the end of the week, and then the defect inflow. The next step is the calculation of the motifs and the SIMSAX. And here we use the parameters. Here is where we specify the parameters, so the number of windows, number of beans, and the number of letters in the alphabet. I encourage you to take a look at this publication that shows which parameters are important. And the main part of the script is to execute the SIMSAX, which looks for pairs of different weeks, calculates windows, finds the alignments, creates motifs, and calculates which weeks are covered in which project, which provides us the results, which are twofold. One result is the percentage of one project being covered by another project. Here we have the similarity of project A to project B, which is 96%, and project B to project A, which is 100%. We could also visualize that in a diagram, which is the code for this in this part of the workbook, and plot it. And here, as we see, we could see different motifs being found in different projects. So if you look at this motif in the first project, it was found in the second project over here, which is not entirely exact, but it's very similar. Or if we look at another motif, this is another motif. As you see, it starts a bit differently, and it's been found in a different place. And the number of motifs that we have found is quite large, so we can just scroll down. We could also take a look in the fact that we have, for instance, one motif from project being found in several other places in another project, like over here. We could also see that sometimes the motifs are linked to one another, so that one motif starts directly after the other, after another one, and could be found in the project again. Now, as you see, there's a lot of those diagrams, really a lot of those diagrams. So presenting this is a challenge, and when presenting that, we could use a bit of a different visualization, which I will show you on the slide in a second. In order to evaluate this method, we have chosen a number of projects from the Eclipse Foundation as objects. We'll look at their defect info profiles, or in this particular case, we actually chose Git commit trends. As you see, they are somehow different, but not entirely different. And we have chosen a number of pairs to compare. So we compared Eclipse JDT core to JDT UI, JDT core to platform, and platform to JDT UI. In order to be able to say something about SIMSAX, we also compared this method to other methods that could be used in the same context. So what we could do is we could use hierarchical clustering with the Euclidean distance, where we basically compare two different trends and say how far those lines are from one another. But this method has a number of different issues. For example, the trends have to be very aligned. If they are just slightly misaligned, it could be very problematic. Or we could get results that are not really reflecting the reality. We could also use the dynamic type warping, which is another method which does not require the commit trends or the defect inflows to be so aligned as to the Euclidean distance, but still is very sensitive to, for example, differences in the total, in the peaks or in total number of defects reported over a week. And when we apply those different methods, we could get those results. This diagram A is an example diagram for the pair, for the first pair, comparing Eclipse JDT Core with JDT UI. And as you see, the number of weeks covered is quite high, but not all of the weeks are covered. If we compare that to the Euclidean distance, basically it says that all weeks are either very similar to one another or very different. Or if we use dynamic type warping, we could see that it's better than the Euclidean distance, but still compares a number of different weeks to one another, given a specific distance threshold. And if we look at the numbers, we could see that the week coverages differ a bit. If for the other methods, they basically say that almost all weeks could be found in other weeks. In our method, it shows that not all of them. So on average, it's 70%. But if we look at the first pair, I showed you that 67% of the weeks in the previous diagram was only 67% of the weeks was found in the second project, and 70% of the second project could be found in the first project. So this is the comparisons that I'm referring to. And of course, they do look similar, but there are some differences over there. So to finalize, we would like to take three different takeaways. For the first, Git commit trends and defect inflow profiles tell a lot about the projects, much more than you could think. They are very cheap sources and very objective sources to compare projects. And with our methods, we could help you to quantify similarities for that. You can find a bit more information about this in our papers. The first one about parameters, the second one about comparison between different methods, and the third one about applying this method to evolving different processes. And finally, we encourage you to take a look at the Software Center website. Thank you.